Section 5.1, Newton's laws of motion. So here our main objectives are to discover how force affects the motion of an object in general, to differentiate between contact and field forces, those two types, to explain any correlation between motion and net external force, to determine the net external force and talk about acceleration in terms of its mass and force, and then identify and explain some action-reaction pairs. So first we'll start with the definition of force, which is necessary to even look into Newton's laws. And a force, generally speaking, could be something that's thought of as a cause of acceleration. And what we're talking about here for this cause of acceleration is we're saying, well, what makes the object's velocity change, right? Because obviously acceleration being caused means there has to be a change in velocity, because acceleration is defined as the change in velocity over time. So if you have a force that causes acceleration, then a force must also cause a change in velocity. And generally speaking, we call this either a push or a pull. Our unit of measurement is called a Newton, and a Newton is the SI unit for force, whereas in English we think of that as a pound. It's a measurement of weight, really, in that sense of pounds in the US, but when we think about weight is also a force, just a force due to gravity. So Newton and pound are the two types of units we think of for SI in English. And a Newton is comprised of a kilogram times a meter per second squared. And we'll see where this comes up in a little while with those units themselves there and how they break down into kilogram meters per second squared with one of Newton's actual laws. Now the two types of forces we have here are contact and field forces. And contact is self-explanatory. You need contact between two objects, but a field force, the idea is that it has to be a distance between the two objects, so they're not in contact with another. This object, this confetti, is being pulled up by this balloon due to static electricity. Some examples of contact forces are things like friction, a push or a pull, or something we're going to see called normal force. And examples of field forces, things that act at a distance, think of gravity, right? Gravity between two objects, you jump up, there's a distance between you and the center of the earth still, and it pulls you down. That's a field force. Or simply a magnetic field or an electric field itself. So to start, we'll start with Newton's first law, which really talks about the concept of inertia. So another name for this is called the law of inertia. And the law of inertia really tells us that if something is moving, it wants to remain moving. If it's at rest, it wants to remain at rest. Now, unless this object is acted upon by some outside force, so if you think about an object on the ground, a soccer ball sitting on the ground, it's stationary. It doesn't want to move, so it's not going to move. Now, unless you kick it, right, you kick it forward with some force in that direction, then it'll start to move this way. Now, as it's moving, it wants to keep moving, actually, but because of friction, it eventually would slow down. A good example would be a hockey puck. When you think about a hockey puck on ice, when a hockey puck glides across the ice, we know that it moves with a velocity that really isn't changed as much. And you can see this actually. Zambonis, to test that the ice is smooth enough, people take a puck and actually shoot it around the inner wall of the ice, and it should return to its actual original starting point based on the coefficient of friction that's a result of the Zamboni smoothing out the ice. So Newton's law really tells us that it's going to continue moving if it's moving unless it's acted upon by friction. Now, on Earth or in any planetary atmosphere, you're going to see that there's got to be friction involved because there's a medium. So the object itself will slow down. But if you think about outer space, when you're in outer space and an object is launched or thrown, if there's no outside force acting on that object, then it'll continue to move. So an object in space, when launched, will move forever, but it turns out it'll move with a constant velocity. And the reason for that is going to come up with Newton's second law, and that'll show us why it's a constant velocity and not some accelerated motion. So next, let's take a look at the net external force. And by doing so, we're really looking at the resultant force acting on an object. And to do this, we're going to take a look at the sum of the forces acting in each direction, the x or the y direction. So if we look at a simple object, and an object being pushed to the right, and maybe friction is pushing back to the left, and then a person is sitting down on the object, and then we have, the table pushing back up on the object. We could look at all these forces independently, or we could look at each direction independently. So looking at these two and comparing them, and looking at these two and comparing them. So if, somebody was pushing it to the right, and say this instead of friction was a person pushing to the left now, whichever of these people is stronger, the object would go in that direction. So if this force is, say, 10 newtons, and this force is only 8 newtons, then we know that the 10 Newton force would overcome the 8 Newton force, and therefore this object would simply move to the right in this case. There's usually a balance in the vertical direction if an object is on a surface, so we don't have to worry about these two being different values. Usually they're the same. But in circumstances where they're not the same, we'll see that there's vertical accelerated motion. We could also take a look at the net external force and think about, well, we have the x and the y direction independently, and at the end we could take a look at that overall and put them back together in the same way that we did with displacement. If we think of an object moving to the right and then moving down, we can think of it moving to the right and down with a diagonal or the hypotenuse of a right triangle. And that's the same idea here. If we can find the overall force in the x and the overall force in the y, and let's say we have for an object that overall the object is being pushed to the right with 5 newtons of force and being pulled down with 7 newtons of force, we could think of that as being, just pulled to the right and down like this, and again find that resultant vector by using Pythagorean theorem with 5 squared plus 7 squared equals r squared. So we can take a look at this net resultant force with example 1, and the concept here is that an object's being pulled to the right, it's being pulled to the left, it's being pulled up, and it's being pulled down. And this is not really reasonable for something like a crate. You would wonder, how does this work? So if you want to be really realistic with it, think of a satellite in space, and you have, say a couple astronauts trying to put this in space and into place in space, and each of them exert forces in different directions. So again, this object is being pulled to the right with 82 newtons of force. It's being pulled to the left with 115 newtons of force. So right away off that, you know that it's going to move left, because left is more than right, so therefore it's got to move to the left. It's being pulled up with a force of 565 newtons, and being pulled down with a force of 236 newtons. So this wouldn't really happen if you were an object sitting at rest on a table, because again, these would most likely be balanced if it's at rest on a table, because there'd be no vertical motion going on. So again, think of this as again, a satellite in space being positioned by 4 astronauts all trying to position it. So because the overall force will be to the left and up, because left is greater than right and up is greater than down in this case, we know that this object will move in this direction, in the upward left direction, or you could say the northwest directional. So to figure out our overall forces, or the net external force, simply sum the forces together. So in the x direction, we've got negative 115 plus 82, and that equals negative 33 label of newtons. And in the y direction, we've got negative 236 plus 565, and that's going to sum together to give us 329 newtons. So as a result, since there's again a positive y and a negative x, we go up and we go over this way. So that's why it's going to be northwest. How would you find the overall resultant in this case? Well, if you wanted to figure out the overall resultant, F, we could think of the x direction being 33, the y direction being 329, and we could use Pythagorean theorem to solve that and determine the overall force. In addition to that, if we wanted to figure out the angle at which the force is being applied, we could solve for theta here by saying that the tangent of theta is equal to the opposite over adjacent, and then use the tangent inverse function to determine the angle theta. The overall resultant in this case, r, using Pythagorean theorem, would be 330.7 newtons, and theta would turn out to be approximately 84.3 degrees. Again, why is this such a great value? Because most of the force is applied in the vertical direction, very little in the horizontal, just like we saw with velocity, displacement, projectile motion. If there's more velocity in the y direction, the angle was always greater than 45, and the angle turns out to be 84.3. Why is this number so close to this number? Because 33 squared is insignificant compared to 329 squared. So as a result, if we really drew this triangle to scale, we would see that 33 would be like this, and 329 would be at a length like this. So our hypotenuse, although looking like it's rather long, is still going to be only about the length of the actual height, or a little bit more, because it must be. So we see that 329 is only slightly less than the hypotenuse of 330.7. So the next topic we have to look at is mass and the concept of what makes up an object, and not in size, because that would be really volume, but actually in matter. So how much matter there is that makes up the object. And this is the traditional way of thinking about mass, and that's what you defined it as in your earlier science classes and most likely in your middle school courses. But I also want to take a look at this concept of mass being a measurement of inertia. And there's a really simple example to think about this. If you think about a golf ball and a baseball separately, if you think about how much force it would take to move a golf ball versus a baseball. And if you think about a golf ball takes much less force. It doesn't really desire to stay at rest very much. Here's your golf ball, and you could tap it very lightly. It would move very easily. And then you take something like a baseball, or even more exaggerated, like a bowling ball. And again, I'm not looking at just size, even though they are different in size also, but the mass is what's different. To move a bowling ball, you apply the same force you apply to a golf ball. It's not going to move very easily. You could say that the bowling ball has more inertia, or it has more mass, the desire to stay at rest, whereas the golf ball itself has very little inertia. It doesn't have as much desire to stay at rest as the actual bowling ball does. A simple mechanical application of this would be seen in a traditional seatbelt. And this is how seatbelts lock, and the locking mechanism works when you apply the brakes. Think about when you apply the brakes in a car. Usually your body wants to fly forward. And traditionally, if you don't have the seatbelt on, what'll happen if you slam on the brakes? You might even, you see stories of people going through windshields because their body wants to continue moving because of inertia, but due to the car braking, the car itself stops, but your body is moving at a certain velocity, so it continues to move forward, and therefore that's how you can get injured, which is why you wear your seatbelt in a car. Well, let's look at the mechanism behind it. What we can see here is that there's actually a mass that's underneath the actual seat of the car. And when the car stops, this mass, in addition to your body being here wanting to fall forward, the mass slides forward. Since the mass is attached to a pin here, and that pin is attached to this rod, as the mass slides forward, this pin also moves forward. And you'll see the rod, instead of being vertical, the rod is now acting at an angle because this mass has slid forward, and now the rod is at an angle. When the rod pivots about this pivot point, the rod itself engages what's called a ratchet, and the ratchet itself is able to only rotate in one direction because of the gear teeth and the way that they're set up. So this rod engages a gear tooth, and when the actual seatbelt wants to pull out like this because the object wants to slide forward, it pulls on this, and the actual seatbelt itself wants to pull up this way. So as a result, the ratchet would turn in this direction, in the counterclockwise direction, in order for the seatbelt to extend and the person to fly forward. Well, it prevents it from doing that by the teeth engagement here. You can see that this tooth, or this single tooth of the ratchet, engages with the actual rod itself, preventing it from rotating in the counterclockwise direction. And what's cool to notice also really is that none of this is electronic. All of it is simply mechanical, and it's using a mechanical mechanism that simply has a mass sliding forward. So with inertia alone, it could cause a locking mechanism to engage without any sort of electronic backup system needed. So next we're going to take a look at some data, and this data is, imagine you had an object here, okay, that you have a hook on the end of it, and then you take a little spring scale, and you hook a spring scale to that, and the spring scale is able to measure some data output, and you apply force to the spring scale. Now this force is measured the entire time with an electronic output, and then the actual acceleration of the object can be measured using a simple what's called accelerometer that's mounted on top of the object. As a result, the data from this is conclusive. You can see here that the acceleration is always going to be around a third of the net force. Every single time we can see that this multiplied by 3 gives us this. So we could say that there's a factor of increase of 3 for all of these scenarios. So it's clear to see that the net force acting on an object is proportional or directly related to the acceleration by some factor. But the question becomes, what is this factor? So let's use a little bit of dimensional analysis in units to figure out what this factor is. So the first way to think about this is that, again, the net force is proportional to the acceleration. Therefore, we could also say simply that F is equal to Ka, where K is some constant of proportionality. So our question is, what is this K? It was a 3 a moment ago. We had this statement. We wrote F equals 3A, because 3 was our factor of increase. So to determine what the 3 really represents, let's take a look at our units. And the units of force are measured in newtons. We don't know the units of 3 or K, our constant of proportionality. The units of acceleration are meters per second squared. So as a result, if we look at this, we could see, well, newtons earlier were defined as kilogram times meters over second squared. And that equals blank times meters over second squared. So all that's missing here is clearly what? Oh, kilograms. That's what belongs over here for this to make sense logically, right? An equation has to have the same thing on both sides. So even if we look at the dimensions or the units of an equation, that also has to match up. So kilogram meter per second squared, kilogram meter per second squared. As a result, what must this be? This must be a measurement of mass. And this is what gives us Newton's second law. So Newton's second law tells us that an object's acceleration is directly proportional to its net external force, and that's seen right here, and that is inversely proportional to the object's mass, and that's seen right here. But we saw it a moment ago written like this, and this is the traditional way you're going to see it written in most of your textbooks. The reason it's written this way is because it's actually very obvious. You could think, right, you apply more force, it's going to accelerate more. But if the object has more mass, it's going to accelerate less. So these are inversely related, whereas these are directly related. The thing that we want to really point out here is this key, that Newton's second law, F equals ma, can work in each direction independently. So if we can find the sum of all the forces, or the net force, right? The net external force means the sum of the forces. If we could find the sum of all the forces acting in the x direction, we could set that equal to the mass of the object times its acceleration in the x direction, and as well as the sum of the net force in the y direction equaling the mass times the acceleration in the y direction. To see this, let's take a quick look at a mathematical example. So we have a space shuttle where astronauts experience accelerations of almost 4 g's, 35 meters per second squared, almost 4 times that of Earth, Earth being 9.81. What force does a 75 kilogram astronaut experience during this acceleration? And this is a very simple example. So we start quickly with our acceleration defined as 35 meters per second squared. Our mass defined as 75 kilograms. With those two things alone, we can see that with F equals ma, the force acting on the object is simply a product of 75 kilograms times an acceleration of 35 meters per second squared. These units have to be newtons because a newton is defined as a kilogram meter per second squared. And we'll see that it's 2,625 newtons of force. So although we don't know what this is in pounds, right? We don't have a conversion necessarily right now. We could see that since this is 4 g's, you feel like your body weighs almost 4 times that of its normal weight on Earth, and that's the acceleration you feel when you're taking off in a space shuttle. In our next example, we want to take a look at, Newton's second law with a little more complicated twist to it, where we can see that we can use kinematic formulas to help us find the acceleration necessary to find the actual net force acting on the object, or the object's mass in this case. So we start with the question that an object is dropped from rest. It happens to be a bowling ball from the top of a building. Now, this would really hurt somebody. I don't know why somebody would actually drop an object like this from the top of a building, but for scientific experimentation, it makes sense to actually measure. The building's height is 11 meters. It hits the ground after a second and a half, and the question is, what is the mass of the ball itself? If the overall force felt by the object, or the bowling ball in this case, is negative 74 newtons. So we start by listing our givens and unknowns. We know that F equals negative 74 newtons. The time it takes is 1.5 seconds. The height of the building is 11 meters, so it's going to fall 11 meters. So I'll put y equals negative 11 meters. We know that the initial velocity is going to be 0 meters per second. Again, because it's initially at rest, it's dropped. And our question is, determine the mass of the object. So to determine the mass of the object, we can recognize that we're going to use F equals ma, but there's no a anywhere in this problem. So the first thing we have to really do is figure out what is a. So to figure out a, we're going to go right away to our kinematic equations. So if I want to figure out what a is, I can think, all right, well, a. Let's go ahead and use our equation that says y equals VIYT plus 1/2 AT squared. And again, we're doing this because we don't really know if this is dropped on Earth. Maybe this is an experiment that's happening on another unknown planet. Or you would do this on a planet, or on the moon, for example. If you can measure this data, you could determine the acceleration due to gravity on the actual moon. So we have the y is negative 11. We are looking for a. We know t is 1.5. VIY is 0 because it's dropped from rest, so this entire thing goes to 0, and we result in y equals 1/2 AT squared. Now, to solve for a, we'll multiply by 2 to get rid of the 1/2. We get AT squared, and then we'll divide by t squared. So we end up with 2y over t squared equals a. Plugging in, we're going to end up with 2 times negative 11 meters all over 1.5 seconds, and that's squared. And therefore, this gives us negative 9.7 repeating, or negative 9.78 approximately. So we can see here that this is definitely on Earth, but it's probably not at normal elevation, or else it would be negative 9.81, or maybe this is taking into account some air resistance as well. Either way, it really doesn't matter. It just proves to us that we are indeed on Earth. So we can now, well, no matter what planet, we can use this formula, but we can now use these numbers here. We know that we're looking for the mass of the object, so the mass is simply the force over the acceleration. So the net force was negative 74 newtons, and that's over negative 9.78 meters per second squared. This will give us a mass of approximately 7.6 kilograms. In example 4, we're going to take a look at an example where an object accelerates from one velocity to another in a given time period, thus undergoing acceleration. Right away you think about, okay, velocity changes from this to this, there has to be acceleration. And here we're going to see that we're trying to find the net external force acting on the object. Well, we're given the mass, we need also the acceleration still to find the net external force. So again, for a problem like this, we've got VI is 6 meters per second. We don't know if it's horizontal or vertical for now, so it really doesn't matter actually. VF in this case is 15 meters per second. The time period is 10 seconds, and the object's mass is 25. We can, for the most part, though, assume that it is horizontal, or else we'd know the acceleration if we're on Earth, but we don't even know if it's on Earth, so we're just going to assume we know nothing in this case, and we'll figure out, well, what is the acceleration? So therefore, then we can figure out what is the force acting on this object. And if this object is a person, then the force pushing is, the force of friction between your shoe and the ground pushing off. If this is a car, then this is the force of the engine pushing forward and turning the axle, and therefore the tire gripping the road. So this force could be a result of many different things dependent upon the scenario, at hand here. But we know alone that we have the change in velocity and the time period, so we can find acceleration with the change in velocity over the time period. So we know it's final minus initial. So there's final minus initial over the time period of 10. So that's going to be 9 over 10, or 0.9 meters per second squared. Once that value is known, it's simple to calculate the force. F equals ma, so there's mass times acceleration, and therefore we can calculate the overall force acting on the object, which is approximately 22.5 newtons of force. So Newton's third law tells us that for every action there's an equal and opposite reaction. And we're going to explain this example just theoretically now, but we'll see this taken into account a little bit more mathematically in the next sections to come. So for here, we're going to see the idea that, every force really just comes in pairs. And the simplest way to think about it is the Earth with a person standing on it. So this is clearly out of proportion, but there's the person standing on the Earth. And when the person jumps, this person jumps into the air, suddenly they're elevated maybe to here, again, way out of proportion. And when they're elevated in the air like that, you get pulled back down because of your weight. And at first, it seems like, oh, this doesn't make sense that they come in pairs, because if the Earth pulls me down, I'm pulling on the Earth also. And actually, that is what's happening. So the Earth pulls us down with a certain amount of force, F, and that's our weight. We usually call that Fg. Well, what's happening actually is that the person is also pulling the Earth up with the same force. But we recognize this, that the pairs coming into play, that's force of gravity, and maybe we'll call this the force of the person on the Earth. And those two things are equal and opposite to each other. But the force of gravity pulling down on an object is that mass of that object times the acceleration acting on that object pulling down. Well, the acceleration is negative 9.81, or in this case, let's just say 9.81 for magnitudes in this case. And the mass of a person might be, let's say, for example here, 50 kilograms. And that's approximately, we multiply that by 2.2 to get pounds, so a little over 100 pounds. Well, that's the mass of a person. Well, the mass of the Earth, let's take a look at what that value is. On the order of 5.9 times 10 to the 24th power. So how is this mathematically possible for this equation to be true? Well, the acceleration that goes here has to be a very, very, very small number. Again, think about this. The product of these two numbers, 50 times around 10, say it's around 500, right? It's not really 500, but approximately 500. Well, for this number to be approximately the same thing over here, this is such a large value that this value has to be so small. So although the Earth pulls down on a person and a person pulls back on the Earth, you know what? The Earth pulling down causes you to accelerate pretty quickly. but you pulling back up on the Earth causes the Earth to accelerate with almost zero acceleration or insignificant acceleration. Now, the way to think about this, or another extension of this, and this is a question that's been posed before, is what if everybody on this side of the Earth at the same time jumped? Right? All these masses pulling upward, would it cause enough acceleration if we sum together all the masses of all the people on the Earth? Well, think about it. Even if there's 6 billion people on the Earth, or whatever it is, half of that, let's say, for this half of the Earth, this hemisphere, so say 3 or 4 billion, whatever the number is, 4 billion times 50 is still not going to be anything when compared to 5.9 times 10 to the 24 billion. That's on the order of 10 to the, 9? So this number is going to still be much smaller than 10 to the 24. So even with everybody moving or jumping at the same time, that mass is not enough to really cause a significant acceleration on the Earth itself.